Application of higher-order differential equations in vehicle suspension systems. Vehicle suspension systems provide a smooth ride and maintain vehicle control even on rough roads. If the vehicle suspension is poor, it fails to absorb vibrations from the road, leading to excessive bouncing and discomfort. To model and improve suspension performance, engineers use higher-order differential equations. But what exactly is a differential equation, and why is a higher-order one needed here? A differential equation relates a quantity to its rate of change. Like population growing, disease spreading, chemical concentration changing, or radioactive material decaying, all changing over time. In a suspension system, the car's motion depends on its position, speed, and acceleration, all changing over time, so we use a second-order differential equation to model it accurately. Modeling suspension, mass spring damper system. To study suspension behavior, engineers use a mass spring damper model. The mass represents the car body, the spring determines stiffness, and the damper resists vibration. This system is governed by a second-order differential equation of the form m into d square x by dt square plus c into dx by dt plus kx is equal to f of t. The suspension equation provides the displacement x of t, showing how the car responds to a bump, including how far it moves and how quickly it settles. Sample problem equation setup. Let's look at a practical example. A 250 kilograms mass connected to a spring with stiffness 20,000 N by M and a damper with 1000 Ns by M. This setup leads to the second-order differential equation. Solving this, we get the general solution. From this solution, engineers calculate key values like natural frequency, damping ratio, settling time, and final displacement. This shows the system is underdamped, with the displacement settling at x is equal to 5 centimeters after oscillation. Let's visualize how this behavior looks over time. The graph animation shows how the suspension starts with high bounces that gradually settle into a stable position. This insight helps engineers fine-tune spring stiffness and damping to optimize both comfort and stability under real-world conditions. Final thoughts: engineering comfort and stability. A poorly tuned suspension causes excessive bouncing and instability. In contrast, a well-tuned system absorbs vibrations smoothly and keeps the ride steady. Engineers achieve this by applying higher-order differential equations to design effective suspension systems. To summarize, engineers use these mathematical models to design safer, smoother, and more responsive vehicles.